In this video, we are going to discuss about the introduction to MOS transistor. So on completion of this topic, students will be able to explain the electrical properties of MOS transistor and they can explain the DC and transfer characteristics of a CMOS inverter. So this has the integration levels of small scale integration, medium scale integration, large scale integration, very large scale integration, ultra large scale integration and very high gigantic scale integration. So while seeing about the CMOS technology, so this is widely used to form the circuits in various applications. Today we can see the computers, CPUs, cell phones, they are using the CMOS to have different advantages. That is, this can offer low power dissipation, high speed, noise margins will be very high, and also they can operate in wide range of sources, and also this provides the voltage to be fixed. So while we are discussing about this type of transistor which is available in the metal oxide semiconductor field effect transistor, these transistors are a sandwich that is consisting of semiconductor layer, that is usually a slice or wafer, or it can be a crystal, or it be a layer of silicon dioxide. So you can see the structure of MOSFET. So here this MOSFET contains three layers. One is metal gate electrode, next is insulating oxide layer, next one is p-type semiconductor. So this MOS structure which forms the capacitor with the gate and the substrate, or the two plates and the oxide layer that acts as a dielectric material. So this thickness of this dielectric material is usually between 10 nm and 50 nm, and also the carrier concentration and the distribution will be within the external voltage applied to the gate and the substrate terminal. So to now understand the structure of the MOS, first we are considering the basic electric properties of this p-type semiconductor substrate. So here you can see the NMOS and the PMOS transistor having the three terminals, that is drain, source and gate. So next is the structure and the operation of MOSFET. So when you are seeing this one, see the structure of the MOSFET is, this MOSFET consists of the MOS capacitor with two PN junctions that is placed close to the channel region, and this region is controlled by the gate voltage. To make both this PN junction reverse biased, substrate potential which we are keeping here lower, that is it will be very lower than the other three terminal potentials. So if the gate voltage, if you are increasing beyond the threshold voltage, for example VGS is greater than VT, means this inversion layer will establish on the surface and this N-type channel will form between the source and the drain. So this N-type channel will carry this drain current according to the VDS value. So this occurs in the three regions, which is linear region, saturation region and cutoff region. So in linear region, when VDS is equal to 0, this thermal equilibrium exists in the inverter channel region, and drain current ID value will be equal to 0. Now if you are giving some small drain voltage, means that is 0, for example a constant value 0 is applied, means a drain current will be proportional to the VDS value, and this will start to flow from the source to the drain to the channel. So this channel gives a continuous path for the flow of the current from the source to drain. So this mode we call it as linear region. So in the case of the saturation region, so if we consider the saturation region, here if you are increasing the VDS value, means then the charges in the channel and the channel depth will decreases at the end of the drain, and here the channel charges in this channel will reduce to 0, which we call it as pinch off point. Okay, so this cross sectional view of the N channel MOSFET, which we can see in this figure. So here this occurs at the depleted surface from near to the drain. So when you increase the drain voltage, the depletion region will extend to the source. So this region we call it as saturation region. Here the electrons coming from the source to the channel end that enter into the drain to depletion region, and they are accelerated towards the drain in the high electric field. So you can see the gradual channel approximation. So gradual channel approximation means here you are considering a cross-sectional view of N-channel MOSFET. So you can see that it is operating in the linear mode. So the source and the substrate are connected to the ground. Here this voltage, when you are setting this gate source voltage to a voltage greater than the threshold voltage means for creating the channel between the source and the drain means this direction is perpendicular to the surface and the that is perpendicular to the surface, and it is the direction is parallel to the surface. So you can see the source with respect to the channel voltage will be constant, and the threshold is also produced between the channel region is constant. So that you can see in the gradual channel approximation. The graph is given here. So when there is a great change in the VCEs, then Vs is equal to 0 value, and when Vgs is greater than the threshold voltage, and Vgd is equal to Vgs minus Vds, which is greater than the V threshold voltage. You can see the saturation region, linear region, and cutoff region here. So his questions on the introduction to MOS transistors. What are the necessary conditions for the different regions of operation in CMOS inverter? Thank you.